Okay, so ladies and gentlemen, we're going to get started. Now, I stand before you, a very sick man, so I'm glad there's a good corridor here. I didn't want to sacrifice this week's classes, but please do be cautious around me, and I will, I get into these bouts of coughing, so if needed, I will don this mask. And proceed to lecture you in a masked fashion. So I hope you'll accommodate that. Hopefully that won't be required, but it's good you keep a certain distance here. I will have office hours after this, but we'll try to hold them at opposite ends of my office if people want to attend. Now, a couple of questions before we begin. We have a couple interesting things to cover today, but I did get some requests today, several in fact, for extensions on the exploratory topics. And I want to make it clear a couple things to the class. First of all, I'm happy to grant extensions to exploratory topics for a couple days, okay? And normally that means for 2 days to the next class session, if possible. I recognize that these exploratory topics are sometimes challenging, and I recognize that they are competing at this time of the term, particularly with lots of other classwork. So I'm happy to be somewhat accommodating in those regards. But I do want to reiterate that the main purpose of these topics, the main goal, is actually not to get you to solve the challenge. It's actually get you to engage with it. In other words, to try it out. So if you're spending more than an hour on it, you may be spending more time than it's worth. And I have asked the marker to be most generous when you hand in things. If it looks like you've given it a try, a serious try, give you full marks, okay? So the goal here is not to come up with a solution, to work hours on it, to achieve that, which I recognize is the standard goal for many other classes, including many in our department. But the goal is instead to get you to try to think about it. And if you're running into challenges and you're fighting with them, just having done that will help you learn more from the lecture. And that's really the goal of these things. It's not to have you solve them. So if you have a very incomplete attempt and it's not yet working, hand it in. Hand it in, as far as I'm concerned, rather than spending a lot of other hours, trying to get it to work. These are challenges that are designed to sort of make you try to think about the issues, come up with, try to identify the barriers you're facing that you might not have realized if you just watch slides on the screen. So please, feel free to hand in things that are very incomplete, that are not working, you're not sure if it's what was intended. All those serve the purpose of get you at least to think about it some. So when I show one solution and when I share it with you, you'll be able to appreciate that better. You'll say, oh, that's how we did that, or oh, that was the thing that was getting me stuck. I see, it's this syntax. So, what I'm tempted to do is to suggest in the agile method principle of time boxing, that you allocate an hour, say, to this. You see what you can do in that hour and you hand it in. You hand it in, okay? And if you couldn't get to part B because part A wasn't working, and then what you can do for part B and say I couldn't get it working in part A, fine. I'm asking the marker to give full marks for those sort of things, okay? So just to get you thinking and encountering what your barriers are so that you can better resolve them in class when you see how I did it, and you can read my solutions and learn from them better. Because if you sit back, you've never tried it, everything sounds straightforward. It's really only when you try it, that's when you realize the texture of the challenges. Okay, so those are some comments on exploratory topics. And I would say if it's more than an hour you're spending, turn it in. And if you don't get marks on that, come see me, and I'll make sure you get marks. Okay? Okay. So, the exploratory topic for today, I asked you to take the code that we had written last time in a object-oriented fashion, and to update it to use Java's functional features. And I have to apologize because I realized I only posted the slides from last time on Java's functional features after I released this, and I apologize for that. That was an oversight on my part. So last time we had a solution to this exploratory topic challenge for last time, number 7, which involved using an object-oriented technique of polymorphism and overriding to support parameterization of this code by the rule. In other words, to allow us to run the same code with different rules. Okay, and the way we did that is we had the way I did it. I had this code determine arguments, which basically would determine what rule to apply. It was way down here, and it used a dispatch table here, which was a hash table. And basically, when we're parsing arguments, I determined, okay, what rule should we use? Is it the classic rule, or is it some other rule as determined by the name as provided by the arguments, the command line arguments? So it would look it up here. It would say classic or liveness 2 to 4, or whatever. And the way this was accomplished, the way that we sort of had different rules encoded, different rules that we could kind of keep track of in this hash table and pass back the right one, was we had an interface called compute liveness rule that had a method called apply. In this compute liveness rule, this was kind of to represent rules that compute liveness, hence the name. And then we had several particular rules, like this one here, which implemented that interface. Okay, this one implemented that interface. This one implemented that interface. Okay, having implemented that, they could then be passed around polymorphically as one of these guys, as a compute liveness rules, because they implemented this interface. They could be treated as one of these by the Liskov substitution principle, right? So in order to do that, we got the rule, I encoded it in a pair, I extracted the rule here, and then we passed it down. We passed it down to run scenario. We passed down this rule, and run scenario passed it down to update space, and update space passed it down to update cell, and update cell ended up applying it. It applied it by calling the apply method. And that apply method for these different rules does different things. It applies the rule and returns a Boolean. True or false? Is this cell live in the next time step or not? Okay? So in short, we realized this parameterization of the code by rules, allowed the code to run with different rules by using it as a parameter of type compute liveness rule. Does that make sense? Okay, that was last time. This is this time. How do we do it this time? Anyone want to comment? What do we use instead of a subtype of compute liveness rule? We can use a Java 8, begins with an F. It ends with an N. A function. Function. Thank you. Yeah. So we're going to use the Java 8 function. Now so when I encountered this, I actually struggled, as I often do, between the desire for conciseness, concision, as they say, on the one hand, and making things a little bit more transparent. So my actual first cut round with this was to actually it's this one here, was to have this directly be encoded as what's called a by function. What is a by function? Anyone remember from last time?
It takes in two parameters, although you passed in 3 to it looks like.
Yeah, the first two, great. First two are the parameters. The last is the return time.
Okay.
Yeah, and there's other ways to do it for special cases, like if it's an int by function, then there's a special case for that, double, long, etc., where we know it takes in the same and returns the same, but we actually call it an operator. Or if it's an int where it takes in if it returns an int, I think there's a special one for that. In any case, there's special ones for subsets. So I encoded this rule as a bifunction, and I passed down a bifunction here. I actually returned it in the pair, and I extracted it in the liveness rules, and I passed it down here as a bifunction, and way down in the bowels, I then applied it. But I didn't like that. That bothered me. Why does it bother me? Well, because it's not so clear what this bifunction is. We could give it a name that would call it like rule complete liveness, but it wasn't somehow capturing the fact that it's a rule quite as transparently. So in the sort of refactoring this code that I did, I actually had a class compute liveness rule that had internally a bifunction, and you basically pass it a bifunction when it was created, when it was constructed, and then that bifunction would be applied when it needed to do its job. Okay, either of these is fine. I think either of these is a perfectly fine way to do it. But having done this as a class meant that we could go and, for example, we could have compute liveness rule of this, or use rule classic, or which is defined as a static variable up here, or otherwise define these rules down here, which are based on lambda functions. So this is a lambda function right here. So when we build this hash table, we are actually inserting into the hash table a map between a key, which is the name of the rule, on the one hand, and the rule itself, which is created by creating an instance, so compute liveness rule with an appropriate function. Appropriate, in this case, it's specified by a lambda function. In other words, by an anonymous function. Okay, so this is an anonymous function. It takes in something that says whether the current cell is alive and the count of things around it that are live, and returns a Boolean value as indicated by this, okay, by this rule here. So this is a big, long, hairy expression, but I'll sort of map it out here. It looks something like this, okay? If that's true, then this, otherwise this. So that's kind of what this is. This is a lambda expression. It's an anonymous function. It takes in these two guys up here, the Boolean, the integer, and returns back a value as given by this. Okay? And I pass this into compute liveness rule because compute liveness rule, ladies and gentlemen, up here takes in a bifunction as an argument and just stores that away in the instance variable. And then I can say, hey, is this alive in the next time step, and have it return the right thing. So now, instead of passing down, like in this code, something called a bifunction, which might be a little bit confusing when you see the code for the first time, I can explicitly pass down in the code from simulate. I can say, this returns a pair of integer and a compute liveness rule. I can give it a nice name for the class that indicates its function, its job in life, and I can pass it down to run scenario. Here's the liveness rule. Run scenario takes the compute liveness rule, passes it down to update space. Update space passes it down in turn to update cell, and update cell applies it with a nice name. Rather than just apply, it uses a nice name. Is it alive in the next time step? Now, so that's, I was kind of torn about how to do it, whether it's through a bifunction, whether directly, or whether to do it through a class that includes a bifunction. I eventually did this. I'm not sure, frankly, which way I don't have a strong preference for one or the other. It seems to me this is a little bit cleaner. Okay, any question about that before we talk about one aspect of boxing, unboxing?
I was wondering why you decided to use a bifunction instead of a bipredicate.
Yeah.
Good question, because I didn't think of it. I love it. I love it. Okay. If you have any missing take-home exercises, come see me. We'll make sure you get credit. Okay, for at least one or two of them. Much better to do it as a by predicate. So thank you. I spent no more than an hour on this. Yeah, by predicate is better. Why is a by predicate better? This actually gets into my next comment. Why is a by predicate better?
Returns a Boolean already.
Returns a Boolean. Not only does it return a Boolean, you could say, well, this by function returns a Boolean, but actually I would say it returns a different type of Boolean. What is that different type of Boolean? This one returns, by function returns, does it truly return an actual, a true or false directly?
No, just an object.
Returns a reference to a Boolean. So every time this returns something, it needs to actually allocate something and stick a Boolean into there. It actually needs to say, give me some memory, sort of the equivalent of calc, right? And get back some memory, stick a true or false in there just to pass it back. So, you called this function and all you got was a reference to a Boolean. I mean, why go through all this mechanism just to return a stinking Boolean, right? There's a lot of questions about that. And a by predicate would actually return a Boolean value, not a reference. It would return a lowercase Boolean, right? Not an uppercase. And that actually would spare you the need for that allocation. Now, it wouldn't spare you the need for these two, capital B here and integer. And when you're applying this rule, which occurs, ladies and gentlemen, right here. Here, this is a live next time step. This takes in a Boolean, lowercase, so this is actually a value. It takes in int, which is lowercase, and it's actually a value. And it returns a lowercase Boolean, okay? But here, ladies and gentlemen, what we're doing is we are actually calling off to liveness rule to this thing here. And so what's happening? Given that liveness rule expects a capital B Boolean and a capital B integer, what is happening right here? So it's expecting a capital B Boolean, a capital I integer, and we're passing it these things that are lower B Boolean and lower I integer. We're passing it values, and what does it do? It boxes them, ladies and gentlemen. It actually will allocate memory right there. Right there. It'll actually allocate memory and stick in that Boolean that you've provided as a value here. It'll stick it in just like that into a reference to a Boolean. True. And the same thing with the integer. It will stick it in, it'll allocate memory for an integer right there and stick in this integer value, 3, that you've computed for the count around it. It'll actually stick it into this newly allocated memory and pass those references along to this liveness rule. And then the liveness rule will return a what? It will return a reference to a Boolean, hence capital B, and it will unbox it and return it as a lowercase Boolean, in other words, a value. So this is what we call boxing and unboxing. And there's a lot of it in Java, particularly when you're dealing with generics. Generics are type parameterized things like this. It's going to be taking things that are values and sticking them into newly allocated memory and having a reference to it, and vice versa, taking the value out of that and returning it as a value. And that has costs. So that brings us, ladies and gentlemen, to no less than part B. Okay? So let's go take a look at part B of this thing, okay? Here's my exercise 8, and we have solutions here to this. Here we are. Hey, why aren't I seeing the solutions?
as a PDF here. That's odd. Okay. So yeah, I don't know why they're not showing up as a PDF. I'm gonna have to go over to Linux land for a second, I think. Give me a sec here, and I will just call them up in Linux. Okay, no, we don't want to go look at that. We want to go to the take-home exercises 8, and we want to open this guy up. Okay, here we go. Okay, and just for the sake of people viewing online, because they can't see my Linux desktop, I'm going to save this as a PDF and go back into Windows World. Okay, here we go. Boom. There we go. Okay, now we're cooking with gas. Okay, so here's the solutions. So this is what I got. For 100,000 iterations, this is what I got. I ran my Python code that I given to you.
So good.
Sorry?
Python's so good.
Look, goodness is fit for fitness for certain purposes, okay? If you're building a website in Django and it's being accessed over a slow network connection, Python's going to be speedy as you need. If you're going to be doing inner loops, computing simulations, Python you might think twice about having inner loops depending on Python. If you have certain areas of your code which are just calling off to whip fast numeric routines that are implemented already in parallel or in a high performance architecture, Python might be fine to glue those together. It's just kind of glueware to call off to high level functions that are themselves written in a much more efficient language. But Python ain't going to cut it by itself in this context. 100,000 iterations. So that's one extreme. Now the other side is C. And you may recall back in the day, this was, I think, take-home exercise 3, we had 3 versions of C code. One with default optimization. So just default vanilla compilation, no special optimization requested. And then, oh, what about mumble? Okay, there's, this is bad. Okay, pardon me as I go off to Linux land again and go correct this. Okay, so there's evidently a reversal here. This is, hey, oh man, okay, this is what we want. These two are reversed, these guys here. Default, I'm sorry, no, what am I doing? Okay, I am sick. Okay, so indeed, default optimizations took long. Yeah, 98 seconds on my machine. With more aggressive optimization, minus 0.2, which is quite safe optimization. It's just being clever and unwrapping loops, being clever and turning multiplications into additions for each side of a loop, eliminating common sub-expressions. So if you're indexing with the same expression again and again into an array, it'll just compute it once, etc. Perfectly safe optimizations, 16.9 seconds. So that's what, over 6 times, not quite 6 times faster, but it's certainly over 5 times faster, maybe 6 times faster. Yeah, than with no optimizations. Okay, with highly aggressive optimizations, and my recollection is 03 has some risque optimizations that could cause problems because it's inferring certain things. 2 things aren't pointing to the same location or what have you. 6.652 seconds, okay? Now in C, highly aggressive optimizations are a little bit of a risky game. Why do I say that? Why do I say they're risky? There's a lot of times in C where we'd love to do an optimization, but we're not absolutely certain. We're quite confident, but we're not absolutely certain it's safe. Why is that? Because, ladies and gentlemen, C is a loosey-goosey language when it comes to types. If you have any pointer type, you can cast it to a void star, and you can turn into any other pointer type. You can have something that you allocated and you stuck some integers in it, and then you turn into a pointer that thinks that those things you put in there are double precision values. It could think those things you put in there are structures. It could think that the things you put in there are pointers. It's a language that grew up implementing operating systems like Unix, later Linux, and when you're implementing a memory map or a scheduler, what have you, sometimes being able to treat it sometimes as one, sometimes as another is favorable. Just treat it as allocated characters when you're reading it in from disk after it was hibernated, and then you treat it as something very different than characters. But, ladies and gentlemen, because of that, sometimes you can't be sure that two pointers are not pointing to the same thing. You write to one, you think you know what's there, but maybe this other pointer points to that same thing, possibly, because you got it by calling off to some function. Weird things can happen in C. C has the potential for fooling things, for hiding certain dependencies between pointers, etc., that can cause major problems. And as a result, you can't optimize it as effectively with total confidence. You can't optimize it with total confidence as effectively, and you can't parallelize it as effectively, because you're never quite sure, can this be done in parallel with that for certain types of operations. As a result, ladies and gentlemen, while we did get some extra gain, notable gain, over 2.5 times gain for going with O3, with the most aggressive optimization, this came with a certain risk associated with that. And this program was small and so on, but if I were compiling a big program, say a large compiler or something else, somewhere in there O3 might introduce bugs that would have to be found by testing, and then we'd have to roll back optimizations on that module from O3 or turn them off by the command line on a per optimization basis. So you should be aware that this reduction here, as I recall for O3, it comes at a certain risk. Okay, now let's see how Java did. How did Java do? Well, here's our original Java. This was classic OO Java. Not a lot of unboxing needed for the specific case, ladies and gentlemen, of applying our rule. This guy here. For the particular case of applying a rule, we pass these in as lowercase b boolean and lowercase I int, in other words, as values, and we got back nothing less than a value, a boolean. So for the particular purpose of this rule, there wasn't allocation and sticking values in just for the sake of communicating a value. We were actually returning values and taking values in. Okay, and partly because of that, we got a performance that actually wasn't bad at all. I thought actually it was worse than this in my comments to you last time, but this is 22% slower, takes 22% longer than highly optimized C. The difference is, ladies and gentlemen, here, with that top Java one, you are confident it is correct. With C, there's always this niggling concern for aggressive optimizations that maybe you've gone too far. You've gone a bridge too far. You came to some conclusions that aren't sound. Where with Java, the dependencies are clearer. You're not going to be making those assumptions because you don't have loosey-goosey types. Not bad. Less than 25% extra time compared to the most optimized C code. And actually favorable compared to aggressive optimization, fairly aggressive optimization. Pretty good, pretty good. And with Java 8 based rule, Java 8 rule parameterization, with what we just saw there, ladies and gentlemen, with this guy here, compute liveness rule, despite this boxing and unboxing and all this unnecessary song and dance involving boxing and unboxing of values to references and vice versa, we still do pretty darn well. Pretty darn well. And we still handily beat out minus O2.
Is that because of how Java handles like function stacks compared to C?
So C function stacks are you have an interesting set of challenges with them, because with C you can do do some things, the function stack, that are not that safe. And the classic example is in a C standard library, long jump and set jump, which directly operate on the stack. You can have pointers to further up on the stack, even after that's been deallocated and so on. The Java, what's going on with Java here is it's actually being very intelligent about certain types of optimization. It's also being intelligent about bytecode, so that it compiles bytecode. I remember I mentioned the hotspot compiler last time. It actually compiles it to machine code where possible. And it's not eliminating some costs. After all, this is more expensive than O3. But it's getting down those costs to a pretty low level. With the stack, C has some advantages involving stack mapping of data structures that we're not taking advantage of in this code base. So our main data structures here are these big arrays, which whether in C code or in Java code are just allocated once and not put onto the stack, etc. So probably for quite a few programs, C would have an extra leg up yet on the Java, but here it's a pretty limited extra speed up you get with C. And you could probably rewrite, if you really wanted to speed this thing up with respect to raw, close to the metal performance, you could probably rewrite 2 loops in this program with C and get almost all of that speed up from C with the existing advantages of Java in terms of type safety and potential ability to parallelize down the road. So here Java is probably not being showcased for some of its challenges as well as it could be with a larger program, but it is impressive what the performance is. Other questions or comments? Okay, so ladies and gentlemen, these are my results. Engage and share some of the results of your own. Okay, so give it a try. But these were the findings that I have. And here Python, well, this version of Python, I actually had a version 3 Python thing that might have had a different performance trade-off as well. But this was Python 2, and I had it over 1,000 times slower than optimized C, than the most optimized C. And nearly 1,000 times slower than the Java. Ooh. Ew. Yeah. Okay. So, comments to the take-home exercise. Any questions related to that? Again, give it a shot for an hour. Hand in what you got. Say if you can't do things. I'll try to make sure that that's given full credit. Okay? Okay. So, ladies and gentlemen, those are some comments on performance.